Welcome to the first lecture in our series on Bitcoin and cryptocurrencies. I want to start by introducing the four lecturers who are going to be speaking in the series. The first lecturer is Joseph Bonneau. He's a postdoctoral researcher in computer science at Princeton University. The second lecturer is me, Ed Felton. I'm a professor at Princeton in computer science and in the Woodrow Wilson School. The third lecturer is Arvind Narayanan. He's a computer science professor at Princeton. And fourth, our special guest lecturer is Andrew Miller. He's a PhD student in computer science at the University of Maryland. There will be 11 lectures in total. In this lecture, number one, we're going to do two things. First, we'll introduce some cryptographic primitives that turn out to be necessary for talking about cryptocurrencies. In particular, we'll talk about cryptographic hashes and digital signatures, and we'll talk about some of the ways in which those are used to build cryptocurrencies. And then at the end of the lecture, we'll start talking about cryptocurrencies, and I'll give some examples of simple cryptocurrencies that illustrate some of the design challenges that we need to deal with. I want to apologize for covering the cryptographic material at the beginning. Unfortunately, we have to eat some of our vegetables a little bit in order to lay groundwork for the cryptocurrency stuff. So if you came for the cryptocurrency stuff, let me assure you, first of all, that we will get to it in this lecture, and that having laid the groundwork in this lecture, there's going to be a lot more specifically cryptocurrency-focused material in later lectures. All right, so let's get to it. In segment 1.1, we're going to talk about cryptographic hash functions. We'll talk about what they are and what their properties are. And then later we'll move on and talk about what their applications are. So a cryptographic hash function is a mathematical function, and it has three attributes that we need to start with. First of all, a hash function can take any string as input, absolutely any string of any size. It produces a fixed size output. We'll use 256 bits in this series of lectures because that's what Bitcoin does. And it has to be efficiently computable, meaning given a string, in a reasonable length of time, you can figure out what the output is. So that's a hash function, but we're going to need hash functions that are cryptographically secure. The cryptographic properties of hash functions are a complicated topic in general, but we're going to focus here on three particular properties, and I'll explain in a minute what those are. In particular, that the function is collision-free, that it has a hiding property, and that it's puzzle-friendly. And for each of these, I'll talk about what the property is, what it means, and then I'll talk about why it's useful to have a function that has that property. So first, collision-free. So the first property that we need from a cryptographic hash function is that it's collision-free. And what that means is that it's impossible, nobody can find values x and y such that x and y are different, and yet the hash of x is equal to the hash of y. And so if we look at the operation of the function as depicted by one of these red arrows, here's x and h of x, and here's y and h of y, then nobody can find a situation like this, that you have an x and y that are separate, and yet when you hash them, they hash to the same value. Now, one thing to notice is that I said nobody can find. I didn't say that there is no collision. Because if you think about it, there has to be a collision. Collisions do exist, and to understand why that is, we can use this diagram. Over here on the left, I'm depicting all of the possible inputs to this function, which can be a string of any size. And over here, I have all of the possible outputs, which has to be a string of 256 bits in size. So the right-hand side here, the outputs, there are only 2 to the 256 possibilities. Over here, there are more possibilities. And so if you think that every point over here on the left is going to be mapped by an arrow to some point on the right, you can see that as you go from all the points over here on the left into the right, it has to get crowded. And in fact, that there have to be multiple values over here on the left that map to the same output over here. In fact, in general, there will be a very large number of possible inputs that map to any particular output. So collisions do exist. I said before, nobody can find a collision, and that's the key question. We know collisions exist. The question is, are there any collisions that are findable by regular people using regular computers? Okay. Now, to make things even worse, I said that it has to be impossible to find a collision. Let me tell you how to find a collision, because there's a method that's guaranteed to work. And the method works like this, that we're going to pick 2 to the 130 randomly chosen inputs over on the left cloud of that previous diagram. And if we pick those 2 to the 130 randomly chosen inputs, it turns out there's a 99.8% chance that at least 2 of them are going to collide. And so this is a very simple method for finding a collision. It works no matter what the hash function is, but of course the problem is that this takes a very, very long time to do. you have to compute the hash function 2 to the 130 times. And that's, of course, an astronomical number. This method works no matter which hash function we're using. There's still a 99.8% probability that this works, and if it doesn't work, just try it again. It'll probably work the next time. But this doesn't really matter. And the reason it doesn't really matter is that this procedure takes 2 to the 130 steps in order to get to that high probability. So we can say something like this. We can say that if every computer ever made by humanity was computing since the beginning of the entire universe up to now, the odds that they would have found a collision is still infinitesimally small. So small that it's way less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds, which didn't happen. Okay, so we know how to find a collision, but this method takes too long to matter. The question is there some other method that could be used on a particular hash function in order to find a collision? And that's the question that is harder to answer. Is there a faster way to find collisions? Well, for some possible values of hash functions, of course there are. For example, if our hash function were to simply take the input modulo 2 to the 256, that is, it just selected the last 256 bits of the input, then we would know an easy way to find a collision. One collision would be the values 3 and 3 plus 2 to the 256. So for some possible values of the hash function, it's very easy to find a collision. For others, we don't know. Now, one thing I need to note is that there's no hash function in existence which has been proven to be collision-free. There are just some that people have tried really, really hard to find collisions and haven't succeeded. And so we choose to believe that those are collision-free. Okay. Now, what good does collision freedom do us? If we can assume that we have a hash function that is collision-free, then we can use that hash function as a message digest. And what I mean by that is the following, that if we know that x and y have the same hash, then it's safe to assume that x and y are different. Because if someone knew an x and y that were different that had the same hash, of course that would be a collision. Since there's not a collision that we know of, then knowing the hashes are the same, we can assume that the values are the same. And this lets us use the hash as a kind of message digest. Suppose, for example, that we had a file, a really big file, and we wanted to be able to recognize later whether another file was the same as the file we saw the first time. Right? So one way to do that would be to save the whole big file, and then when we saw another file later, just compare them. But because we have hashes that we believe are collision-free, it's more efficient to just remember the hash of the original file. Then if someone shows us a new file and claims that it's the same, we can compute the hash of that new file and compare the hashes. If the hashes are the same, then we conclude that the files must have been the same. And that gives us a very efficient way to remember things we've seen before and recognize them again. And of course, this is useful because the hash is small. It's only 256 bits, while the original file might be really big. So hash is useful as a message digest, and we'll see later on in this lecture and in subsequent lectures why it's useful to use hashes as message digests. So the second property that we want from our hash function is that it's hiding. And the property that we want is something like this, that if we're given the output of the hash function, that there's no feasible way to figure out what the input x was. The problem is that this property doesn't exactly hold. And to understand why that's the case, let's look at this example. So here, what we're going to do is an experiment where we flip a coin, and if the result of the coin flip was heads, we're going to return the hash of the string heads, and if the result was tails, we're going to return the hash of the string tails. And now we're going to ask someone who didn't see the coin flip but only saw this hash output to figure out what the string was that was hashed. That, of course, is going to be easy. It's easy in this scenario to find what the input string was. It's easy to find x. You simply compute the hash of the string heads and the hash of the string tails, and you see which one you got. And so in just a couple of steps, you can figure out what x was. So the reason this example failed, that is the reason why an adversary was able to guess what the string was that there were only a couple of possible values of x. And so if we're going to have a hiding property like this, it needs to be the case that there's no value of x which is particularly likely. That is, x has to be chosen from a set that's in some sense very spread out, so that this method for the adversary of just trying all the possible values of x, or just trying a few values of x that are especially likely, is not going to work. So the hiding property that we are going to need to set up is a little bit more complicated. And the way we're going to fix this problem with the common value x, like heads and tails, is we're going to take the x and we're going to put next to it, we're going to concatenate it with it a value r, which is chosen from a distribution that's really spread out. And so this h of r concatenated with x, that means take all the bits of r and put after them all the bits of x. And so what we're going to say is, given the hash of r together with x, that it's infeasible to find x, and that this will be true in the formally stated property that if r is a random value chosen from a distribution that has high min entropy, then given the hash of r concatenated with x, it's infeasible to find x. And what does high min entropy mean? Well, it captures this intuitive idea that r is chosen from a distribution that's really spread out. And what that means specifically is that there's no particular value that r could have had that would occur with more than a negligible probability. So for example, if r is chosen uniformly from among all of the strings that are 256 bits long, then any particular string was chosen with probability 1 in 2 to the 256, which is truly a negligible value. So as long as r was chosen that way, then the hash of r concatenated with x is going to hide x. And that's the hiding property that the hash function will be deemed to have. Okay, now let's look at an application of that hiding property. And in particular, what we want to do is something called a commitment. And this is kind of the digital analogy of taking a value, a number, and sealing it in an envelope and putting that envelope out on the table where everyone can see it. Now, when you do that, you've committed to what's in the envelope, but you haven't opened it. It's secret from everyone else. Later, you can open the envelope and get out the value, but it's sealed. So commit to a value and reveal it later. We want to do that in a digital sense. So to be more specific about what is the API that we're going to provide here, the commitment API looks like this, that there are two things you can do. First, you can commit to a message, and that's going to return two values, a commitment and a key. Think of the commitment as the envelope that you're going to put on the table, and the key as a secret key for unlocking the envelope. Then later, you allow someone else to verify, given a commitment and given a key which you've told them in the meantime, and the message, they can verify that that commitment, key, and message really do go together, and this will return true or false. Okay, now to seal MSG in an envelope, what we do is we commit to the message, and that returns a commitment and a key, and then we publish the commitment. That's putting the envelope on the table. Now later, to open the envelope, what we're going to do is publish the key and the message that we committed to, and then anybody can use this verify call with the commitment that we published previously, the key and message that we just announced, to check the validity of our opening the envelope. Okay. And the property, of course, we want from this is that it behaves like sealing an envelope. And in particular, the two security properties are these. First, given COM, the commitment, the envelope on the table, that someone just looking at the envelope can't figure out what the message is. The second property is that it's binding, that when you commit to what's in the envelope, you can't change your mind later. That is, it's infeasible to find two different messages such that you can commit to one message and then later claim that you committed to another, and the whole thing will verify. Okay, so how do we know that these two properties hold? Well, first we need to talk about how we're going to actually implement commitments. And the way we're going to implement commitments is like this. That in order to commit to a value message, we're going to generate a random 256-bit value and call it the key. And then we're going to, as the commitment, return the hash of the key concatenated together with the message. And as the key value, we're going to return h of this key. And then later, to verify, someone is going to compute this same hash of the key they were given, concatenated with the message, and they're going to check whether that's equal to the commitment that they saw. Okay, so this is a way of using hash functions both in the commitment and in the verification. So now the security properties, if we go down to the security properties that were at the bottom of the previous slide, and we just plug in the definitions of how we're going to implement this here, that is, this used to say COM, given COM, infeasible to find message, we just plug in what COM is. COM is the hash of key concatenated with message. And similarly down here, this is what happens when we take what was written there before and plug in the definition of verify in COM. Okay, so now what these properties become, the first one is given h of key concatenated with message, it's infeasible to find message. Well, it turns out that that's exactly the hiding property that we talked about before. Key was chosen as a random 256-bit value, and therefore the hiding property says that if we take the message and we put before it something that was chosen from a very spread out distribution, like I said, a random 256-bit value, then it's infeasible to find the message. So this is exactly the hiding property. And this one down here turns out to be exactly the collision-free property. So that if someone can find two messages which have the same hash like this, well, then they have an input value here and an input value there that are different, and yet those have the same hash. And so because of the two security properties we've talked about for hashes so far, this commitment scheme will work in the sense that it will have the necessary security properties. Okay, so that's the second security property of hashes, that they're hiding, and the application of that is commitments. The third security property we're going to need is that they're puzzle friendly. And this is, again, a little bit more complicated, but let me just go through it a bit by bit. That for any possible output value y that you might want from the hash function, we're going to use y as an output value of the hash later, that if k is chosen from a distribution that has high min entropy, that is k is chosen randomly from some set that's super spread out, then there's no way to find an x such that the hash of k and x is equal to y. So what this means is basically that if someone wants to target the hash function, if they want it to come out to some particular output value y, that if there's part of the input that is chosen in a suitably randomized way, that it's very difficult to find another value that hits exactly that target. So the application we're going to use of this is we're going to build a search puzzle. And what that means is we're going to build a mathematical problem which requires searching a very large space in order to find the solution, and where there's no shortcuts, a way to find a good solution other than searching that large space. That's a search puzzle. To be more specific, the idea is that if we're given a puzzle ID, which is chosen from some high min entropy distribution, that is some very spread out probability distribution, and we're given a target set y, which someone wants to make the hash function fall into, then we want to try to find a solution x, so that if we hash the puzzle ID together with the solution x, we get a result that's in the set y. So the idea is y is a target range or set of hash results that we want. ID specifies a particular puzzle, and x is a solution to the puzzle. And the puzzle-friendly property here implies that there's no solving strategy for this puzzle, which is much better than just trying random values of x. And so if we want to pose a puzzle that's difficult to solve, that we can do it this way, as long as we can generate puzzle IDs in a suitably random way. And we're going to use that later when we talk about Bitcoin mining. That's the sort of computational puzzle we're going to use. Okay, so we've talked about three properties of hash functions and one application of each of those. Now let me talk just very briefly about the particular hash function we're going to use. There are lots of hash functions in existence, but this is the one Bitcoin uses, and it's a pretty good one to use. It's called SHA-256, or SHA-256, and it works like this. Basically, it takes the message that you're hashing, and it breaks it up into blocks that are 512 bits in size. The message isn't going to be, in general, necessarily exactly a multiple of the block size, so we're going to add some padding at the end. And the padding is going to consist of, at the end of the padding, a 64-bit length field, which is the length of the message in bits. And then before that, it's going to consist of a 1-bit, followed by some number of 0 bits. And you choose the number of 0 bits so that this comes out exactly to the end of a block. So once you've padded the message so that its length is exactly a multiple of the 512-bit block size, you then chop it up into blocks, and you then execute this computation. You start with a 256-bit value called the IV. That's just a number that you look up in a standards document. And then you take the IV and the first block of the message, you take those 768 total bits, and you run them through this special function C, the compression function, and out comes 256 bits. You now take that with the next 512 bits of the message, run it through C again, and you keep going. Each iteration of C crunches in another 512-bit block of the message and mixes it in sort of logically to the result. And when you get to the very end, you have consumed all of the blocks of the message plus the padding. The result is the hash. That's a 256-bit value. And it's easy to show that if this function C, this compression function, is collision-free, then this entire hash function will also be collision-free. The other properties are a little bit more complicated, so I won't talk about them here. Okay, so we've talked about hash functions. We've talked about what hash functions do. We've talked about 3 properties of hash functions and applications of those properties, and the specific hash function that we use in Bitcoin. In the next lecture segment, we'll talk about ways of using hash functions to build more complicated data structures that are used in distributed systems like Bitcoin. In section 1.2, we're going to talk about hash pointers and their application. A hash pointer is a kind of data structure that turns out to be used a lot in the systems that we're talking about. And a hash pointer is basically a simple thing that we're going to take a pointer to where some information is stored, and we're going to, together with that pointer, store a cryptographic hash of the information. So whereas a regular pointer gives you a way to retrieve the information, a hash pointer is going to let us ask to get the information back. And it's also going to let us verify that the information hasn't changed. So a hash pointer tells us where something is and what its value was. Okay, and we're going to draw a hash pointer in diagrams like this. That we're going to have h of, and then an arrow that points to something. So anything drawn like this, think of it as being a hash pointer to this thing. It's a pointer to where it's stored, and it's also the hash of the value that this data had when we last saw it. And we can take hash pointers and we can use them to build all kinds of data structures. So a key idea here, take any data structure, a linked list, a binary search tree or something like that, and implement it with hash pointers instead of pointers as we normally would. For example, here's a linked list that we've built with hash pointers. And this is a data structure that we're going to call a blockchain. So just like a regular linked list where you have a series of blocks and each block has data, as well as a pointer to the previous block in the list, here the previous block pointer will be replaced with a hash pointer. So it says where it is and what the value of this entire previous block was. And we're going to remember the head of the list like this, just as a regular hash pointer. Okay. And a use case for this, for a blockchain like this, is a tamper-evident log. That is, if we want to build a log data structure that stores a bunch of data so that we can add data onto the end of the log, but if somebody goes later and messes with data that is earlier in the log, we're going to detect it. That's what the tamper evidence means. So to understand why a blockchain gives us this tamper evident property, let's ask what happens if an adversary wants to go back and tamper with data later that's in the middle of the chain. Okay, so let's assume that an adversary wants to tamper with this block down here. He wants to change the data here, and he wants to do it in such a way that we, the holders of the hash pointer at the head here, won't be able to detect it. All right, so the adversary changed the contents of this block, and therefore the hash here, which is a hash of this entire block, is not going to match up. Because the hash function is collision-free, it must be the case that the hash of this block is now different. And so we could detect the inconsistency between this data and the hash pointer that we remembered before. Or we could do that unless the adversary also tampers with the hash pointer. If he tampers with this hash pointer, then he makes these two match up. But now he's changed the content of this block. And what that means is that when we come back later and hash the contents of this block, it's not going to match the hash that we remembered before because the contents of the block has changed. And so we're going to detect the inconsistency between the contents of this block and this hash, unless the adversary also tampers with the block over here on the right. But now when he does that, the hash of this block is not going to match the hash that we remembered up here and the hash that we're holding on to. And this the adversary can't tamper with because this is the value that we remembered as being the head of the list. And so the upshot of this is that if the adversary wants to tamper with data anywhere in this entire chain, in order to keep the story consistent, he's going to have to tamper with hash pointers all the way back to the beginning, and he's ultimately going to run into a roadblock because he won't be able to tamper with the head of the list. And so what this means is that just by remembering this hash pointer, we've essentially remembered a kind of hash, a tamper-evident hash of the entire list all the way back to the beginning. And so we can build a blockchain like this containing as many blocks as we want, going back to some special block at the beginning of the list, which we might call the genesis block. And that's a tamper-evident log built out of a blockchain. Now, another useful data structure that we can build using hash pointers is a binary tree. We can build a binary tree with hash pointers, and this is called, in the jargon, a Merkle tree, after Ralph Merkle, who invented it. And the idea is this. Suppose we have a bunch of data blocks, which we'll draw across the bottom down here. we're going to take pairs, consecutive pairs of these data blocks, and for these two data blocks, we're going to build a data structure here that has two hash pointers, one to each of these blocks. And similarly all the way across. We'll then go another level up, and this block here will contain a hash pointer of these two children down here, and so on all the way back up to the root of the tree. And then just like before, we're going to remember just the hash pointer up here at the head of the tree. And we can then, if we want, traverse down through the hash pointers to any point in the list, and we can make sure that the data hasn't been tampered with. Because just like I showed you with the blockchain, if an adversary tampers with some block down here at the bottom with the data, that will cause the hash pointer that's one level up to not match, so he'll have to tamper with that. And therefore, he'll have to tamper with the hash pointer one level up from there. And therefore, he'll have to tamper with the hash pointer one level up from there. And eventually, he'll get up to the top where he won't be able to tamper with the hash pointer that we've remembered. So again, any attempt to tamper with any piece of data across the bottom will be insured against by just remembering the hash pointer at the top. Now, another nice feature about Merkle trees is that unlike the blockchain that we built before, that if someone wants to prove to us that a particular data block is a member of this Merkle tree, all they need to show us is this amount of data. So if we remember just the root, and someone wants to convince us that this block is in the Merkle tree, they need to show us this block, and we can verify that the hash matches up. And then they need to show us this block, and we can verify that the hash of this matches that. They can show us this block, we verify that the hash of this block matches this hash pointer, and then they show us the data. And just by verifying the hashes up to the root, we can verify that this data block was in the Merkle tree. So that takes about log n items that we need to be shown, and it takes about log n time for us to verify it. And so with a very large number of data blocks in the Merkle tree, we can still prove membership in a relatively short time. Okay, so Merkle trees have various advantages. One advantage, of course, is the tree holds many items, but we just need to remember the one root hash, which is only 256 bits. We can verify membership in a Merkle tree in logarithmic time and logarithmic space. That's nice. And there's a variant, which is a sorted Merkle tree. That's just a Merkle tree where we take the blocks at the bottom and we sort them into some order, say alphabetical, lexicographic order, or numerical order, or some order that we agree on. Now, having done that, once we've sorted the Merkle tree, now it's possible to verify non-membership in a Merkle tree. That is, we can prove that a particular block is not in the Merkle tree. And the way we do that is simply by showing a path to the item that's just before where that item would be and just after where it would be. And then we can say, look, both of these items are in the Merkle tree, they're consecutive, and therefore there's no space in between them. There's nothing in between them, and so the thing that we're trying to prove non-membership of can't be there. All right, so a Merkle tree is a binary search tree built with hash pointers. We can do logarithmic time membership proofs, non-membership proofs if we sort the tree, and it's very efficient. More generally, it turns out that we can use hash pointers in any pointer-based data structure, as long as the data structure doesn't have cycles. If there are cycles in the data structure, then we won't be able to make all the hashes match up. If you think about it, in an acyclic data structure, we can sort of start near the leaves or near the things that don't have any pointers coming out of them, compute the hashes of those, and then work our way back sort of toward the beginning. But in a structure with cycles, there's no end that we can start with and compute back from. So for example, a directed acyclic graph out of hash pointers, and we'll be able to verify membership in that DAG very efficiently, and it will be easy to compute. So this is a general trick that you'll see over and over throughout the distributed data structures and throughout the algorithms that we talk about later in this lecture and in subsequent lectures. In segment 1.3, we're going to talk about digital signatures. This is the second cryptographic primitive along with hash functions that we need as building blocks for the cryptocurrency discussion later on. So a digital signature is supposed to be just like a signature on paper, only in digital form. And what that means is this. What we want from signatures is two things. First, that just like an idealized paper signature, only you can make your signature, but anyone who sees your signature can verify that it's valid. And then the second thing you want is that the signature is tied to a particular document. so that somebody can't take your signature and snip it off one document and glue it onto the bottom of another one. Because the signature is not just a signature, it signifies your agreement or endorsement of a particular document. Okay, so the question is, how can we build this in a digital form using cryptography? So let's get into the nuts and bolts. Here's an API for digital signatures. There are three operations that we need to be able to do. The first one is we need, in the beginning, to be able to generate keys. And so we have a generate keys operation, and we tell it a key size. How big in bits should the keys be? And this produces two keys, SK and PK. SK will be a secret signing key. This is information you keep secret that you use for making your signature. And PK is a public verification key that you're going to give to everybody and that anybody can use to verify your signature when they see it. Okay. The second operation is the sign operation. So the sign operation, you take your secret signing key and you take some message that you want to put your signature on, and it returns sig, which is a signature. It's just some string of bits that represents your signature. And then the third operation is a verify that takes something that claims to be a valid signature and verifies that it's correct. It takes the public key of the signer, it takes the message that the signature is supposedly on, and it takes the supposed signature. And it just says yes or no, is this a valid signature? Okay, so these three operations, these three algorithms constitute a signature scheme. And I'll note that the first two can be randomized algorithms. The verification won't be, it will always be deterministic. And in fact, if you think about it, generate keys had better be randomized because it ought to be generating different keys for different people. Okay, so the requirements for the signatures at a slightly more technical level are the following two requirements. First of all, that if a signature is, that valid signatures will verify. If a signature is valid, that is, if I sign a message with SK, with my secret key, that if someone then later tries to validate that using my public key and the same message, that will validate correctly. So this says that that signatures are useful at all. But then the second thing you want is that it's impossible to forge signatures. That is, an adversary who knows your public key, who knows your verification key, and gets to see signatures on some other messages, can't forge your signature on some message that he wants to forge it on. And in order to explain this property in a little bit more detail, it's normally formulated in terms of a sort of game that we play with an adversary. So the game, I'll depict it here with this diagram. So over here on the left, you have the challenger, who's a TV judge, and the challenger is going to test a claim by an attacker. The attacker claims that he can forge signatures, and we're going to test that claim, and the judge will pass judgment on it. The attacker here, this guy is actually Whit Diffie, who is one of the inventors of digital signatures, of the concept of digital signatures, and a distinguished cryptographer, so I thought I'd let him play the attacker role here. Okay, so the game works like this. The first thing we do is we use generate keys to generate a secret key, a secret signing key, and a public verification key that match up. Now we give the secret key to the challenger, to the judge, and we give the public key to both parties, both to the challenger and to the attacker. So the attacker only knows information that's public. He only knows the public key. And his mission is going to be to try to forge a message. The challenger knows the secret key, so he can make signatures. Right? Now, if you think about a real-life application, and a real-life attacker would be able to see valid signatures from their would-be victim on a number of different documents. And maybe the attacker could even manipulate the victim into signing innocuous-looking documents, if that's useful to the attacker. So in our game, we're going to allow the attacker to get signatures on some documents of his choice. And we see that in the diagram like this. The attacker is going to send over a message M0 to the challenger, and the challenger is going to sign that message and send the signature back. The attacker can look at that, scratch his head a little bit, and send over another message, M1. The challenger will sign that. And we do that for as long as the attacker wants. The attacker can send over any sequence of messages he wants and get signatures on them. Once the attacker is satisfied that he's seen enough signatures, and we're going to let him see only a plausible number, then he's going to pick some message M that he wants to forge a signature on, and he's going to try to forge a signature. And of course, there's a rule that says that this M, this message that he's trying to forge a signature on, isn't one of the messages that he's already seen. Because it would be really easy for him to send over a valid signature on M0. I mean, we sent him a valid signature on M0 earlier. So he's going to pick some other message that he hasn't seen a signature for already, and he's going to send over what he claims is a signature on that message. And then the question is, can he succeed? So the challenger is going to run the verify algorithm, use the public verification key and on that message and the signature that the attacker provided, and is going to check whether it verifies. And if it does verify, if this returns true, then the attacker wins. The attacker has forged a message. And so this game is what we use to define what it means for a digital signature scheme to have the unforgeability property. And if we want to get really precise, what we say is that the attacker's probability of winning this game is negligible, and that that's true no matter what algorithm the attacker is using. In other words, we're going to say that the signature scheme is unforgeable if, no matter what algorithm the attacker is using, the attacker has only a negligible chance of successfully forging a message. And if we have that property together with the much easier property that valid messages verify, then we have a digital signature scheme that is suitable. Okay. Now, there's a bunch of practical things that we need to do to turn that algorithmic idea into a more practically implementable signature mechanism. For example, the algorithms we talk about are randomized, at least some of them will be, and so we need a good source of randomness. And the importance of this really can't be underestimated. Band randomness will sink you, your algorithm will be insecure. And I'll just point out here that attacks on the source of randomness are a favorite trick of intelligence agencies, and those are the people who know what kinds of attacks are likely to be successful. In practice, there's a limit on the message size that you're able to sign because real schemes are going to operate on bit strings of limited length. The fix to that is simply to use the hash of the message rather than the message itself. That way the message can be really big, but the hash will be only 256 bits. And because hash functions are collision-free, it's safe to use the hash of the message as the input to the digital signature scheme rather than the message. And by the way, a fun trick, which we'll see used later, is that you can sign a hash pointer. And if you sign a hash pointer, then the signature covers or protects the whole structure. Not just the hash pointer itself, but everything it points to and everything it points to. For example, if you were to sign the hash pointer that was at the end of a blockchain, the result is that you would effectively be digitally signing the entire contents of that blockchain. That's a useful trick that we'll see used later. Okay, now let's get into the nuts and bolts. Bitcoin uses a particular digital signature scheme that's called ECDSA. That's the elliptic curve digital signature algorithm, and it's a US government standard. And we won't go into all the details of how ECDSA works. It relies on some extremely hairy math. And trust me, you don't want to see all the details of how that works. You can look it up if you're interested. So we'll skip that. One thing I'll note, though, is with ECDSA, good randomness. I said this before, but I'll say it again because it's really essential. Good randomness is especially essential with ECDSA. If you use bad randomness in generating keys or even in signing, you probably leaked your private key. It stands to reason that if you use bad randomness in generating a key, that the key that you generate is maybe not secure. But it's a quirk of ECDSA that even if you use bad randomness just in making a signature using your perfectly good key, that also will leak your private key, and then it's game over. So we need to be especially careful about this in practice. This is a common mistake. So that completes the discussion of digital signatures as a cryptographic primitive. And then in the next segment, we'll move on and talk about some applications of digital signatures that will turn out to be useful in building cryptocurrencies. In segment 1.4, we'll move on, having covered digital signatures, and talk about a nice trick that we can use that goes along with digital signatures. And the useful trick is this. The idea is to take a public key, one of those public verification keys from a digital signature scheme, and equate that to an identity. That is an identity of a person or an actor in a system. So if you see a signature that verifies correctly, that is, if you see a signature such that you can verify with someone's public key that that is a signature on a particular message, then you can think of that as that public key saying the message. You can literally think of a public key as kind of like an actor or a party in a system, and that they can make statements by signing those statements. And so if you think in that mindset, then this public key is like an identity. It's an actor who can do stuff in the system. And if you think about it then, for someone to speak for PK, that is for someone to be able to make statements that will be seen as coming out of PK's mouth, you have to know the matching secret key, SK. And so if you know the secret key that corresponds to the public key, PK, then you can sign messages with that secret key. And what you're doing essentially is making statements on behalf of that public key. And that means that there is an identity in the system which only you can speak for. And of course, that's what you want an identity to be. Something that one person can speak for or on behalf of that everybody can see. All right. So if we're going to treat public keys as identities, one of the consequences of that is that you can make a new identity whenever you want. If you want to make a new identity, you just do this. You create a new random key pair, SK and PK, by doing the generate keys operation in our digital signature scheme. And we get out SK and PK. PK is then the public name that you can use. That's the name of that identity, what it's called. Although in practice, you'd probably use the hash of PK because public keys are big. But again, we'll leave that aside as a detail. So PK, or the hash of it, is the public name that you use to talk about the identity. And SK, the secret key, is the information that lets you, the person who generated this identity, speak for the identity. You control the identity because only you know the secret key. And if you generated this in such a way that the public key PK looks random, then nobody needs to know who you are. You can generate a fresh identity that looks random, that looks like a face in the crowd, that only you can control. This brings us to the idea of decentralized identity management. That rather than having a central place that you have to go in order to register as a user in a system, you don't need to get a username, you don't need to inform someone that you're going to be using a particular name. If you want a new identity, just make one. Anybody can make a new identity at any time, and you can make as many as you want. If you prefer to be known by 5 different names, no problem, just make 5 identities. If you want to be somewhat anonymous for a while, you can make a new identity, use it just for a little while, then throw it away. All of these things are possible with decentralized identity management, and there's no central point of control, so that you don't have to have anyone who's in charge of it. The system operates in an entirely decentralized way. And this is the way Bitcoin, in fact, does identity. These identities are called addresses in Bitcoin jargon. And so you hear the term address used in talking about Bitcoin and cryptocurrencies. But what that really is just a public key or a hash of a public key. It's an identity that someone made up out of thin air as part of this decentralized identity management scheme. Now, the obvious question that arises when you're talking about decentralized identity management and people making up these identities is, how private is this? And the answer is, it's complicated. On the one hand, the addresses that are made up this way are not connected to your real-world identity. You can execute a randomized algorithm. It will make some kind of PK that looks kind of random, and nothing exists initially to connect that to who you are. You can do that in the privacy of your own home. So that's good news if you want to be able to act privately. But the bad news if you want to act privately is that if that address, if that identity is making a series of statements over time, if it's engaging in a series of acts over time, that people can see that whoever this is has done a certain series of actions. And they can start to connect the dots. Gee, this person is acting a lot like Joe. Maybe this person is Joe. And so an observer can link together these things over time and make inferences. And so this balance between, on the one hand, there being no initial tie to real-world identity, and on the other hand, that a pattern of behavior of an address emerging over time, and the question of what can be inferred and which dots can be connected, that gets pretty complicated. And that's really the question of privacy in a cryptocurrency like Bitcoin. And there's a whole lecture about that later on. And so I'm not going to steal the thunder of that lecture. I just want to give you an idea of how decentralized identity makes privacy a complicated question. In segment 1.5, we're going to move from talking about cryptography, and we're going to move on to cryptocurrencies. Now, I know that many of you showed up here for the cryptocurrency stuff, and trust me, there will be a lot more cryptocurrency material in future lectures. Unfortunately, we needed to eat some of our cryptographic vegetables in order to have the background to talk about cryptocurrencies. And now you'll see when I start talking about cryptocurrencies how these pieces fit together and why the cryptographic operations like hash functions and digital signatures are actually useful. All right, so in this section I want to talk about some simplified cryptocurrencies that give us ideas about how systems like Bitcoin work. Of course, it's going to require about 10 more lectures in order to really spill out all of the implications of how Bitcoin works and what that means. But let me talk about some very simple cryptocurrencies to get the discussion started. And first, let's talk about Goofy Coin. Goofy Coin is about the simplest cryptocurrency we can imagine. And it works kind of like this. There are just a couple rules of Goofy Coin. The first rule is that Goofy can create new coins. Goofy can make a new coin whenever he wants, and when he makes a new coin, it belongs to him. So when Goofy makes a coin, it's represented by a data structure like this. Here you have the create coin operation, and there's a unique coin ID that Goofy generated, and then there's a digital signature that was put on it by Goofy, which anyone can verify. So anyone being given this can verify that the signature is valid and that it's a signature of this statement. And new coins belong to Goofy by definition because those are the rules that Goofy made. So that's the first rule. Goofy can create new coins. The second rule of Goofy Coin is that whoever owns a coin can pass it on to someone else. They can spend it. So for example, here we have the coin that I showed you before that Goofy created. And now we're going to take a hash pointer to that coin. And then we're going to create a statement. Goofy's going to make a statement that says, pay this to Alice. Alice is being named by a public key here. Pay to public key Alice the coin that's represented by this hash pointer. And this is also signed by Goofy. Now, Goofy is the one who owned that coin, and so Goofy has to sign any transaction that spends the coin. And once this has happened, now Alice owns the coin. Alice owns the coin, and Alice can prove that she owns the coin because she can present this data structure here, which is validly signed by Goofy and points to a coin that was validly owned by Goofy. And so the correctness of this coin is self-evident in the system. Now Alice can move on, and she can spend the coin as well. So here we have the coin we had before. This is down here at the bottom. We have the creation of the coin signed by Goofy. Now Goofy paid the coin to Alice via this hash pointer, and he signed that. Now Alice is the owner of the coin. Now she can create a statement like this that says, pay this coin to Bob's public key, and here's a hash pointer to the coin. And now Alice signs that. So because Alice was the valid owner of the coin, which we could verify by walking this chain, now we know that this is valid and the coin belongs to Bob. So Bob is now the owner of this coin. So those are all the rules of Goofy Coin. Goofy can create new coins by simply signing a statement that he's making a new coin with a unique coin ID. And then whoever owns a coin can pass it on to someone else by signing a statement saying, pass on this coin to person X. And you can verify the validity of a coin by simply following the chain and verifying all of the signatures along the way. That's Goofy Coin. All right. Now, there's a problem, though. There's a big security problem with Goofy Coin, and we can see it in this structure here. So look at this coin here. This is the coin that Goofy made and then paid to Alice. Alice was the owner of that coin, and there's a problem. Alice paid this coin on to Bob, but now Alice makes another data structure like this, which pays to Chuck the very same coin. And this is signed by Alice. Now, if Chuck doesn't know about this thing up in the upper left, this data structure, let's say Alice just gave that to Bob and didn't tell Chuck. Now Chuck will look at this and he'll think that this is perfectly valid, and now he's the owner of the coin. Chuck has a valid looking claim to be the owner of this coin, and Bob has an equally valid looking claim to be an owner of this coin, and that's a problem because coins are not supposed to work that way. This is called a double spending attack. It's called double spending because Alice is spending the same coin twice. And double spending attacks are one of the key problems that a cryptocurrency has to solve. Goofy Coin does not solve the double spending attack, and therefore Goofy Coin is not secure. So although Goofy Coin is simple and we understand its rules, it won't cut it as a cryptocurrency because it allows double spending. So in order to build a cryptocurrency that is going to be workable, we need to have some solution to the double spending problem. And indeed, the double spending problem is the main design challenge that we face in designing a cryptocurrency. So we need to somehow improve on Goofy coin. And we'll do that by designing another coin, which I'll call Scrooge coin. Scrooge coin is going to be rather like Goofy coin, except it will solve the double spending problem in a particular way. And this coin was created by Scrooge. Okay, so this is a little bit more complicated in terms of data structures, but here's one of the key ideas, that Scrooge is going to publish a history of all the transactions that have happened. This will be a blockchain, that data structure we talked about before, and it will be digitally signed by Scrooge. So anyone can, and it looks like this, of course. It's a series of blocks, data blocks. Each block will have one transaction in it. This block has the transaction with transaction ID number 73. And it has the contents of this transaction, and then there's a hash pointer to the previous block in the history. Okay, and then Scrooge will take the hash pointer, which represents this entire structure, and he'll digitally sign it and publish it. Now anybody can verify that Scrooge really did sign this hash pointer, and then they can follow this chain all the way back and see what is the entire history of all the transactions in the history of Scrooge coin as endorsed by Scrooge. Okay. Now I said here that we put one transaction in each block. We do that for simplicity of explanation, but in practice, as an optimization, we'd really put multiple transactions into the same block, as Bitcoin does. So you can bear in mind as I talk about Scrooge coin that that's the way we'd really do it in practice. So Scrooge publishes this history. What does the history do? Well, the thing the history does for us is it allows us to detect double spending. Because assume Alice owns a coin, and she's going to pay that coin on to Bob. And she's then later going to try to pay that coin on to Charlie. Charlie's going to notice that something is wrong because Charlie will be able to look into the history and see that Alice already paid that coin to Bob. In fact, everyone will be able to see that Alice already paid that coin to Bob. So if she tries to pay that coin to Chuck, then everyone can see that that's a double spend and they'll be able to reject it. Scrooge will reject it, and everyone else will reject it and know that they really shouldn't trust Alice. All right. So in Scrooge coin, there are two kinds of transactions. The first kind is a create coins transaction, and what it does is create new coins. That's like the operation Goofy could do in Goofy coin that makes a new coin. But here, we're going to allow multiple coins to be created in one transaction. So here's what a create coins transaction looks like. It has transaction ID number 73, let's say in this case. Its transaction type is create coins, and then down here there's a list of which coins are created. Each coin is going to have a serial number within this transaction, 0, 1, 2, etc. Each coin has a value. It's worth a certain number of Scrooge coins. And each coin has a recipient, which is going to be a public key who gets that coin as it's created. So this transaction type creates a bunch of new coins and assigns them to people as initial owners. Now we're going to have a concept in Scrooge coin of a coin ID. That refers to a particular coin. So this particular coin here is coin ID 73 because it was created in transaction 73 and it was number 0 within that transaction. Similarly, we have 73 73 and so on. So every coin in Scrooge coin has a coin ID that we can use to refer to it. A create coins transaction is always valid. Why is it valid? Well, because Scrooge said so, and they call it Scrooge coin for a reason. If Scrooge puts this into the history which he signs, then it's valid by definition. We don't need to worry about whether Scrooge is entitled to create coins, just like we didn't need to worry in Goofy coin about whether Goofy is entitled to create coins. The rules of the system, which were created by Scrooge, simply say that if Scrooge wants to make coins, then that's valid. So anything he puts into the history is valid. The second kind of transaction we're going to talk about is a pay coins transaction. And this is a transaction that consumes some coins and destroys them and creates new coins of the same total value, but which might belong to different people. So over here on the left, we have an example of what a pay coins transaction looks like. This is transaction ID number 73, let's say. Its type is pay coins. We have here a list of the coins that this one consumes. All of these coins are being consumed and destroyed by this pay coins transaction. So we're going to add up the value of all of those coins, and then we're going to create a bunch of new coins, down here 0, 1, and 2, etc., just like before in the create coins transaction. Each one has a value. Each one will belong to a certain recipient. And those new coins had better add up to the same total value as the coins that we consumed. And then at the bottom, we have a set of digital signatures. This transaction has to be signed by everyone who's paying in a coin. So if you're the owner of one of the coins that's going to be consumed in this transaction, then you need to digitally sign the transaction to say that you're really okay with spending this coin. The rules of Scrooge coins say that a PayCoins transaction is valid if 4 things are true. First, if the consumed coins are valid, that is, they really were created in previous transactions. Second, that the consumed coins were not already consumed in some previous transaction. That is, that this is not a double spend. Third, that the total value of the coins that come out of this transaction is equal to the total value of the coins that went in. And finally, that the transaction is validly signed by the owners of all of the consumed coins. If all of those things are true, then this PayCoins transaction is valid. Scrooge will accept it. He'll write it into the history, into the blockchain, and everyone will see that this transaction has happened. One thing to note about this scheme is that coins are immutable. Coins are never changed, they're never subdivided, they're never combined. All they are is created once in one transaction and then later consumed in some other transaction. But you can get the same effect as being able to subdivide or pay on or combine coins by using transactions. For example, if you want to subdivide a coin, you can just create a new transaction that consumes that one coin and then produces 2 new coins of the same total value. And if you want, you can give those 2 new coins back to yourself. That's a way that you can subdivide a coin that you own. Similarly, you can combine coins or you can pay on a coin, in effect, by just creating a chain of transactions, each of which pass that value on in the form of a new coin to someone else. So although coins are immutable in this system, it has all of the flexibility of a system that didn't have immutable coins. Okay, now we come to the core problem with Scrooge coin. Scrooge coin will work. People can see which coins are valid. It prevents double spending because everyone can look into the blockchain and see that all of the transactions are valid and that every coin is consumed only once. But the problem is Scrooge. Scrooge thinks this is fine, right? Scrooge says, don't worry, I'm honest. But the fact is, if Scrooge starts misbehaving, then we're going to have a problem. Or if Scrooge just gets bored of the whole Scrooge coin scheme and stops doing the things that he's supposed to do, then the system won't operate anymore. And so the problem we have here is centralization. That although Scrooge is happy with this system, we as users of it might not be. So the central technical challenge that we need to solve in order to improve on Scrooge coin is, can we de-Scroogify the system? That is, can we get rid of that centralized Scrooge figure? Can we have a cryptocurrency that operates like Scrooge coin in many ways, but doesn't have any central trusted authority? In order to do that, we're going to need to figure out how to provide the services that Scrooge provides, but do it in a decentralized way, in a way in which no particular party is particularly trusted. That means we're going to need to figure out how everyone can agree upon a single published blockchain that is the agreed upon history of which transactions have happened. We need to figure out how people can agree which transactions are valid and which transactions have actually occurred. And we need to figure out how we can assign IDs to things in a decentralized way. If we can solve all of those problems, then we can build a currency that is very much like Bitcoin, which is like Scrooge coin, but without a centralized party. But in order to do that, it's going to take a few more lectures, and we hope you'll stick around and watch them. Thanks. I didn't say that there is no collision, because if you think about it, there has to be a collision. Collisions do exist, and to understand why that is, we can use this diagram. Over here on the left, I'm depicting all of the possible inputs to this function, which can be a string of any size. And over here, I have all of the possible outputs, which has to be a string of 256 bits in size. So the right-hand side here, the outputs, there are only 2 to the 256 possibilities. Over here, there are more possibilities. And so if you think that every point over here on the left is going to be mapped by an arrow to some point on the right, you can see that as you go from all the points over here on the left into the right, it has to get crowded. And in fact, that there have to be multiple values over here on the left that map to the same output over here. In fact, in general, there will be a very large number of possible inputs that map to any particular output. So collisions do exist. I said before, nobody can find a collision, and that's the key question. We know collisions exist. The question is, are there any collisions that are findable by regular people using regular computers? Okay, now to make things even worse, I said that it has to be impossible to find a collision. Let me tell you how to find a collision, because there's a method that's guaranteed to work. And the method works like this, that we're going to pick 2 to the 130 randomly chosen inputs over on the left cloud of that previous diagram. And if we pick those 2 to the 130 randomly chosen inputs, it turns out there's a 99.8% chance that at least 2 of them are going to collide. And so this is a very simple method for finding a collision. It works no matter what the hash function is, but of course the problem is that this takes a very, very long time to do. You have to compute the hash function 2 to the 130 times, and collision-free. Okay. Now, what good does collision freedom do us? If we can assume that we have a hash function that is collision-free, then we can use that hash function as a message digest. And what I mean by that is the following, that if we know that x and y have the same hash, then it's safe to assume that x and y are different. Because if someone knew an x and y that were different that had the same hash, of course that would be a collision. Since there's not a collision that we know of, then knowing the hashes are the same, we can assume that the values are the same. And this lets us use the hash as a kind of message digest. Suppose, for example, that we had a file, a really big file, and we wanted to be able to recognize later whether another file was the same as the file we saw the first time. Right? So one way to do that would be to save the whole big file, and then when we saw another file later, just compare them. But because we have hashes that we believe are collision-free, it's more efficient to just remember the hash of the original file. Then if someone shows us a new file and claims that it's the same, we can compute the hash of that new file and compare the hashes. If the hashes are the same, then we conclude that the files must have been the same. And that gives us a very efficient way to remember things we've seen before and recognize them again. And of course, this is useful because the hash is small. It's only 256 bits, while the original file might be really big. So hash is useful as a message digest, and we'll see later on in this lecture and in subsequent lectures why it's useful to use hashes as message digests. So the second property that we want from our hash function is that it's hiding. And the property that we want is something like this, that if we're given the output of the hash function, that there's no feasible way Welcome to the first lecture in our series on Bitcoin and cryptocurrencies. I want to start by introducing the 4 lecturers who are going to be speaking in this series. The first lecturer is Joseph Bonneau. He's a postdoctoral researcher in computer science at Princeton University. The second lecturer is me, Ed Felton. I'm a professor at Princeton in computer science and in the Woodrow Wilson School. The third lecturer is Arvind Narayanan. He's a computer science professor at Princeton. And fourth, our special guest lecturer is Andrew Miller. He's a PhD student in computer science at the University of Maryland. There will be 11 lectures in total. In this lecture, number 1, we're going to do 2 things. First, we'll introduce some cryptographic primitives that turn out to be necessary for talking about cryptocurrencies. In particular, we'll talk about cryptographic hashes and digital signatures, and we'll talk about some of the ways in which those are used to build cryptocurrencies. And then at the end of the lecture, we'll start talking about cryptocurrencies, and I'll give some examples of simple cryptocurrencies that illustrate some of the design challenges that we need to deal with. I want to apologize for covering the cryptographic material at the beginning. Unfortunately, we have to eat some of our vegetables a little bit in order to lay groundwork for the cryptocurrency stuff. So if you came for the cryptocurrency stuff, let me assure you, first of all, that we will get to it in this lecture, and that having laid the groundwork in this lecture, there's going to be a lot more specifically cryptocurrency-focused material in later lectures. All right, and that's of course an astronomical number. This method works no matter which hash function we're using. There's still a 99.8% probability that this works, and if it doesn't work, just try it again. It'll probably work the next time. But this doesn't really matter. And the reason it doesn't really matter is that this procedure takes 2 to the 130 steps in order to get to that high probability. So we can say something like this. We can say that if every computer ever made by humanity was computing since the beginning of the entire universe up to now, the odds that they would have found a collision is still infinitesimally small. So small that it's way less than the odds that the Earth will be destroyed by a giant meteor in the next 2 seconds, which didn't happen. Okay, so we know how to find a collision, but this method takes too long to matter. The question is there some other method that could be used on a particular hash function in order to find a collision? And that's the question that is harder to answer. Is there a faster way to find collisions? Well, for some possible values of hash functions, of course there are. For example, if our hash function were to simply take the input modulo 2 to the 256, that is, it just selected the last 256 bits of the input, then we would know an easy way to find a collision. One collision would be the values 3 and 3 plus 2 to the 256. So for some possible values of the hash function, it's very easy to find a collision. For others, we don't know. Now, one thing I need to note is that there's no hash function in existence which has been proven to be collision-free. There are just some that people have tried really, really hard to find collisions and haven't succeeded. And so we choose to believe that those are. So let's get to it. In segment 1.1, we're going to talk about cryptographic hash functions. We'll talk about what they are and what their properties are. And then later we'll move on and talk about what their applications are. So a cryptographic hash function is a mathematical function, and it has three attributes that we need to start with. First of all, a hash function can take any string as input, absolutely any string of any size. It produces a fixed size output. We'll use 256 bits in this series of lectures because that's what Bitcoin does. And it has to be efficiently computable, meaning given a string, in a reasonable length of time, you can figure out what the output is. So that's a hash function, but we're going to need hash functions that are cryptographically secure. The cryptographic properties of hash functions are a complicated topic in general, but we're going to focus here on three particular properties, and I'll explain in a minute what those are. In particular, that the function is collision-free, that it has a hiding property, and that it's puzzle-friendly. And for each of these, I'll talk about what the property is, what it means, and then I'll talk about why it's useful to have a function that has that property. So first, collision-free. So the first property that we need from a cryptographic hash function is that it's collision-free. And what that means is that it's impossible, nobody can find values x and y such that x and y are different, and yet the hash of x is equal to the hash of y. And so if we look at the operation of the function as depicted by one of these red arrows, here's x and h of x, and here's y and h of y, then nobody can find a situation like this, that you have an x and y that are separate, and yet when you hash them, they hash to the same value. Now, one thing to notice is that I said nobody can find.